Look at integrating with substitution. So basically we want to undo the chain rule. What we want to do is try and recognize that there are two pieces to the function and that one might be the derivative of the other. And that's what we want to try and pick out. So what I'm going to do here, let's just do a bunch of examples here. So I'm looking at two things really. I want to pick one piece of the function, and I'm just going to pick this one just for right now. And then what I'd want to do is find the derivative of it. So the derivative of, here I should say, the derivative of u with respect to x is du dx. And then we have 2x. And then if I want the du and dx on other opposite sides, I'm going to just multiply both sides by that dx part. And then I'm going to be looking in here to see, do I have this anywhere to do a substitution? And I do. So I can rewrite the integral in terms of u and say, hey, I picked u was x squared plus 1. So really I have u squared. And that 2x dx, I can replace that with du. And then I can do the integral. Right, that'll be u cubed over 3 plus c. But then I just want to resubstitute in to be back in the original variable. So instead of u cubed, I would have x squared plus 1 cubed over 3 plus c. And that's all. Right? So here's another one. I could say that u is, and don't write this down, what if I say that u is cosine of 4x? So if I do a derivative here, right, derivative of cosine is going to be negative sine of 4x. Then I have to multiply it by 4 because that chain rule there. But I don't see that anywhere in my integral as it is, right? So that's not going to be a good choice to use for u. So what do we use for x? Because the derivative here would be 4 dx. And if I rewrite this, 4 dx is 4 dx. And then I can rewrite that as cosine of u du. So then my integral is going to be sine of u plus c. And then instead of u, we'll substitute it back into our original variable. So sine of 4x plus c. Let's do some more. Sometimes there's a little bit of different tips and tricks on what u is going to be. If we have trig functions, sometimes it's going to be what is in the parentheses of the trig functions. Occasionally it'll be the actual trig function itself if there's two trig functions involved. Or any groupings. So like in this case, that square root symbol, I would try the 4x squared plus 1 as u, because I could rewrite that as u to the 1/2. And then hopefully my du is going to be what's left, that 8x dx. So let's see, that will give me 8x dx. So I can just substitute that. And then do the integral. So u to the 3/2 times 2/3 plus c. But then we want to be back in the original variable. So 2/3 times 4x squared plus 1 to the 3/2 plus c. Okay. Let's do this one. So let's do u as x squared plus 2. So du is going to be 2x dx. And I can start to rewrite it as u cubed, but then let's see. I have x dx. And in this case, I have x dx. And I have 2 as a multiplier here. So what I can do is I can divide both sides by 2 and make that a 1/2 du. And really that 1/2 I can pull all the way out and then I can integrate. So I have 1/2 times, and that's u to the 4th over 4 plus c. And then we'll just resubstitute in. So instead of u to the 4th, we'll have x squared plus 2 to the 4th. And then 2 times 4 is 8. And then plus c. So sometimes if there's a multiplier out here, we can divide both sides and pull it out. Right? Now let's let u be our denominator in that grouping. So 4x squared plus 3. So then du is going to be 8x dx. But I only want x. Oops. I only want x dx. So I can divide both sides by 8. So I can pull the 1/8 out. And then I have 1 over u to the 6 du. And I can really rewrite that as u to the negative 6. And then I can do my rules as normal. So u to the negative 5 divided by negative 5 plus c. And then we'll put in our variables. Let's go ahead and make that a negative 1/40th. Then I like positive exponents, so I'm going to drop it down to the bottom. So 4x squared plus 3 to the 5th, and then plus c. I just think it looks prettier that way. All right, let's try another one. So how about u is 7 minus 2x cubed? So that du is negative 6x squared dx. And I want just 1x squared. Let's divide both sides by 6. And then I can pull it out. So when I rewrite, it's u to the 1/3 du. And then I can integrate. So let's see, I would add 1, so it's going to be 4/3, and we'll multiply by 3/4, and don't forget plus c. And then the 3 and the 6 can cancel out, right, to be 1/2. So then I'm left with negative 1/8, and then u, 7 minus 2x cubed to the 4/3 plus c. And I don't really need that negative 1 there. I can just leave that negative sign there. And then just to make it pretty, maybe put the 8 in the middle. Right. All right, so maybe we want to try and use some trig identities first, then try u sub. So instead of tangent x, what if we rewrite that as sine over cosine? So here's where we might use u as one of our trig functions. So how about let's do cosine. So du is negative sine of x dx. The only difference is that negative sign. So how about negative and then integral of 1 over u du? And 1 over u goes to natural log of the absolute value of u. So now we have negative natural log of the absolute value of cosine of x plus c. All right, for a similar reason, cotangent, let's rewrite it as cosine of x over sine of x. And this time, let's let u be sine of x. So that du is cosine of x dx. And if I rewrite the integral, I get 1 over u du again. And so I get natural log the absolute value of u plus c, which will give us natural log of sine of x plus c. Right? I think these next ones are also going to be pretty similar. Instead of secant, let's see, I don't want to do 1 over cosine of x dx, because that's not really going to help us, because u would be cosine, so then du would be negative sine of x, and I don't see that anywhere in our function. So that kind of trig sub is not going to work, right? this one is going to be a stretch. Because I somehow would like to get it in terms of a 1 over u du. So in the end, I have natural log of some quantity. Just because that's how it's worked out in the other trig functions. So it means I need to force a fraction. So secant x. Let's see some things that go with secant. Well, the derivative for secant is secant tangent. And then tangent, the derivative is secant squared. So maybe I want some form of that. What if I multiply the numerator and denominator by secant x plus tangent x, right? Whatever I do at the top, I have to do to the bottom. And then maybe if I use u as secant x plus tangent x, let's see if I can force du to be in the function. So secant x, the derivative is going to be secant tangent. The derivative for tangent is going to be secant squared. And I think if I distribute, that'll give me secant squared, and that'll give me that secant tangent. So then I would have 1 over u du. So I can do the natural log, the absolute value of u plus c, and take natural log, resubstitute in u. So secant x plus tangent x plus c, right? So that's a little bit of a stretch. Then we're going to do the same idea for this cosecant, right? So I want some kind of like cosecant and cotangent in there. So we'll probably do the same thing and make that a cosecant x, and then multiply the numerator and denominator by cosecant x plus cotangent x. And then for the same reason, use u as cosecant x plus cotangent x. So that du is, let's see, negative cosecant squared x minus cosecant x cotangent x. So then when I go to rewrite it, I've got 1 over u du, and then the difference is a negative. So I can divide both sides by -1 and pull the negative out. So then I get negative natural log of u plus c. And then I can go straight into substituting in u, which was cosecant x plus cotangent x. Right, so sometimes doing trig substitutions like that can help us to integrate. Right, there's some other things that maybe we want to rewrite or expand before doing. Like sine squared of x. We want to use another trig identity here, or trig substitution, and make, let's see, because sine squared of x, we could use 1 minus cosine of 2x over 2, and then split that up. So I can split that up into 1/2 minus cosine of 2x over 2. So, all right, 1/2, that's going to go to 1/2 x. And then we can probably do a u sub on that one, right? And say that u is 2x, so that du is 2. And then if I divide both sides by 2, I can pull out the 1/2 that was already in there, and then pull out another 1/2 from that substitution and make that a cosine of u du. And I'll simplify as I go here. That's going to be a negative 1/4. And then that's going to give us sine of u plus c, and we'll just re-substitute in. So sine of 2x plus c. Okay, and then maybe here we want to multiply it out. So sine of x plus cosine of x times sine of x plus cosine of x. So that we have, let's see, sine squared of x, and then we'd have sine times cosine, and another sine times cosine, so 2 sine of x cosine of x, and then plus cosine squared of x dx. And then sine squared plus cosine squared is 1. So I've got 1 plus 2 sine of x cosine of x. Can split these and do 1 dx plus 2, which really I can pull the 2 out front and make that sine of x cosine of x dx. And then do a u sub and say that u is sine of x, so that du is cosine of x dx. So the integral of 1 is just going to be x plus c. And then we have 2, and that becomes the integral of, it's just going to be u du, which will make u squared over 2, right? And then plus another c value. I guess we could say this is C1 and C2. We don't know what they would be, right? So I don't want to call them the same thing. So then we get x plus, the 2's will cancel, right? And then I'm just left with u squared, which was sine, so sine of x squared. And then plus, and I'll make it a third constant, because C1 plus C2 is going to be a different constant, right? Okay, so those are all indefinite integrals. So what if we have definite integrals? So we have some bounds on here. So there's a couple ways we could do it. I usually don't change the bounds because I throw everything back into terms of x in the end. But we can change the bounds. So when we turn things in terms of u, we would have to change the bounds to be also in terms of u as well. So with this first one here, if we say that u is tangent of x and du is the secant squared of x, and we rewrite our integral as u du, I need to rewrite these, right? So if x is 0, my new u is going to be tangent of 0. And if x is pi over 4, then my new upper bound is going to be tangent of pi over 4, right? So we'll get 0 and 1. So when we go and do our integration, we got u squared over 2, and we wouldn't do plus c because we have bounds here, and we can say, all right, so now we have 1 squared over 2 minus 0 squared over 2, which is going to leave us with just 1/2. And sometimes, especially with trig functions, it might be easier to change those bounds. And so I'll change the bounds again for b, but then I'll show you like what happens if I don't change the bounds. And yeah. So, all right, this next one, let's make u cosine of 2 theta, so that du is negative 2 sine of 2 theta, d theta. And then I can divide both sides by negative 2. So I really have negative 1/2, and then the integral of 1 over u cubed du, which I can really rewrite that as u to the negative 3. And then my new bounds, right? So if x is 0, u is cosine of 2 times 0, which is, let's see, cosine of 0 is 1. And then if x is pi over 6, u is going to be cosine of 2 pi over 6, which is the same thing as pi over 3, which is going to give us 1/2. So, okay, our new bounds are 1 to 1/2, right? Which actually means we would switch it and make it negative, right? Because our bounds need to go from lowest to highest. So instead of negative 1/2, we'll have positive 1/2 from 1/2 to 1 of u to the negative 3 du. And then I can do the integration. So I've got, what would that be? U to the negative 2 over negative 2 from 1/2 to 1. So it's really going to be negative 1/4. And I'll just drop it to the denominator. 1/2, top minus bottom, 1 squared minus a negative 1/4, and then 1/2 squared. So let's see, that's going to be a negative 1/4. That'll end up being plus. And then 1/2 squared is 1/4 times 4 is 1. So that's just 1. So we'll just make that 4 over 4. And for a final answer of 3/4. Right. So maybe for the trig functions, it's helpful. I'm so used to you put it back in terms of the original variable, so then I don't worry about the extra step of finding the new bounds if I put it back in the original variable. So if I have u is 1 plus x cubed, du is 3x squared dx, which is what I have. So I'm integrating u to the 1/2 du, which would give me u to the 3/2 times 2/3. And then I substitute back in the original, so 2/3, and then u is 1 plus x cubed, and then to the 3/2. Then evaluate it from 0 to 2. So I have 2/3 times 1 plus 2 cubed to the 3/2 minus, if I substitute in 0, so 2/3, 1 plus 0 cubed to the 3/2. So 2 cubed is 8, 8 plus 1 is 9, square root of 9 is 3, 3 cubed is 27, 27 divided by 3 is 9, 9 times 2 is 18, and then 1 plus 0 cubed is 1, 1 to the 3/2 is 1, 1 times 2/3 is 2/3, and then, gosh, what's 18 times 3? 54, 2, 54, so 54 thirds minus 2/3 is 52 thirds, right? I'll do it in another color if I were to have changed the bounds. So if x is 0, u is 1 plus 0 cubed, which is 1. And then if x is 2, let's see, 1 plus 2 cubed is 9. So we'd go from 1 to 9. And then we'd go from this point here. So 2/3 times 9 to the 3/2 minus 2/3 times 1 to the 3/2, which we get the same thing, right? Square root of 9 is 3, 3 cubed is 27, divided by 3, and then multiplied by 2 is the 18, and then minus 2/3. So it's pretty much the same thing. Okay. All right, so we have u can be 1 plus 5x squared. So that du is going to be what, 10x? And then I want to divide both sides by 10. And then in terms of u, that's going to be 1 over u du. And here's where it might be easier to change the bounds because I'm going to deal with natural log, right? So if x is 0, then u is 1, and if x is 1, then u is 6. So we're now going from 1 to 6. So 1/10 natural log, the absolute value of u, and then we can plug in 1 and 6. So 1/10 natural log of 6 minus 1/10 natural log of the absolute value of 1. Well, natural log of 1 is just 0, so we're left with 1/10 natural log absolute value of 6. Okay. Some other techniques we might need to use. Can use long division, which we should, like when we are doing integrals, we should be in like proper form, I guess I should say. So we want the numerator degree to be higher in a sense. So let's do long division first and then see what happens. So we've got x cubed. We can do synthetic, doesn't matter. We can just divide, doesn't matter. So we got 1, 3, -1, -3, and then divide out -1. So we get -1, -2. So it does divide out exactly, and I'm left with x squared plus 2x minus 3. And that's a little easier to integrate than doing all of that, right? So we get x cubed over 3 plus 2x squared over 2 minus 3x plus c. And then that'll cancel out the 2 over 2. So really I am left with that x squared. Right? All right, let's see if we can do this one. So let's just do long division with this one. X squared plus 0x minus 4 divided by x squared plus 1. So I would need 1, and that would give me x squared and x. I don't know why I said that. And 1. And then I subtract everything over, and I'm left with 0x minus 5. And I can't divide any further, so my integral would now become 1, and then minus 5 over x squared plus 1. I can integrate the 1, right? That's just going to leave me with x. And then here, it's on your reference sheet, but we haven't talked about it just yet. But remember 1 over x squared plus 1, that was our inverse trig derivative. It's the inverse tangent. And so I can do minus 5 and then inverse tangent of x plus c. Don't stress too much about that one because we're going to do more with inverse trig in a later lesson. But yeah. All right, and maybe doing a u sub right away is not going to help, right? If I do u as x squared minus 8x plus 16, well, du is going to be 2x minus 8, and I don't see that anywhere else in our function. But I think if we complete the square, and maybe we don't have to complete the square with this first one, we probably have to do it with the second one. Like, let's factor that denominator. I think we can make that an x minus 4 squared. And then u could be x minus 4, du would be 1, right? And I can pull the 5 out as a multiplier, so I'm left with 1 over u squared du. Or really, u to the negative 2 du, so that I get 5 u to the negative 1 over negative 1 plus c, right? So negative 5 and then u, and I'll just drop it to the bottom, x minus 4, and then plus c, right? And then this is another one that really we would use this with inverse trig stuff, and you'll see what I mean in a minute. Because we want to make this a perfect square so that we can do some things with it, right? So if I do x squared plus 2x plus 2 and act as if I'm going to make it, perfect square, right? You take half of b. Let's see. I guess really I'd move, or how I've always done it, I've moved the 2. And then take half of b, square it, and add it to both sides. So half of b is 2. Or b is 2. So half of b is 1. 1 squared is 1. So we'll add it to both sides. So then, okay, I can factor this now. That's going to be x plus 1 squared. And then this is negative 1. And I can really add that back over. So if I rewrite my integral, it's 3 over x plus 1 squared plus 1. And then this we'll recognize soon is inverse trig, right? Because we have in the denominator, we've got x squared plus 1. But really we have something else. So we can use 1 over a, and then inverse tangent of u over a plus c. So again, don't stress with this one. 3 I can pull out as a multiplier, and then I have 1 over a, which in this case is 1, because this is a squared, or sorry, u squared plus a squared. So a is 1, and then inverse tangent of u, which is x plus 1, over a, which is also 1. So really I'm left with 3 times inverse tangent of x plus 1 plus c. Okay. And that is all for this substitution section. Again, we'll do more with the inverse trig in a later lesson. But if you have any questions, let me know.